Okay, so we need to finish up the 3-2 notes that we started in class, and I can't remember which class, one of them I had one tiny formula left that we hadn't done, and then in both we just didn't get to the examples. So the only formula that I think it was fourth period that maybe we didn't get to it is part of the range rule of thumb, but it's the um, way to estimate the value of the standard deviation. So, range rule of thumb estimate, and we would really only use this if they tell us to, because we have much more precise formulas. So unless we need to, we wouldn't use this. This is really something that we use if we need to have something that's a very quick and, not necessarily very accurate estimate. So the sample standard deviation can be estimated if we need to by taking the range, which is max minus min, and then dividing it by 4. Again, we would never use this formula unless they specifically say use the range rule of thumb to estimate the standard deviation. Or, of course, if they didn't actually give you the data values, but you knew the max and the min. So those are really the only cases we would use it. So the data that we're going to use for our examples today are the same pieces of data used in 3.1 for the diastolic measures. So I'm just going to write them out here because I already had them in order in the 3.1 notes. So these are the diastolic blood pressure readings. And we had 52, 58, 64, 272s, a 74, 76, 280s, an 82, an 88, and a 90. So these were the diastolic readings. This is our data from that sample. And so we're going to do some various things based on this information. So first thing we're going to do is related to this formula. We're going to use that range rule of thumb to estimate the standard deviation, and then subsequently also the variance. So within doing that, we actually find all 3 of our measures of variation, because in order to use the range rule of thumb, we have to calculate the range, which is our 3rd measure. So the range we get by taking the max minus the min. So in this case, since they're in order, the max is 90, the min is 52. So that gives us 38 then for the range, and our formula for the range rule of thumb says that I can estimate that sample standard deviation by taking the range, which is 38, and dividing it by 4. Now, we didn't write them out here as a rule because it's going to be the same for all 3 of these. And it's the same as really what you had in section 3.1 as well. Our rounding rule for the standard deviation and for the variance is that we would round to 1 decimal place further than the original data. So this comes out as 9.5, which is 1 decimal place further, so that's actually pretty good. We're going to leave it just like that. So our estimated sample standard deviation is 9.5. To find the estimated sample variance, then, we would take our sample standard deviation and we would square that. So if you take 9.5 squared, you get 90.25, but again, our rounding rule says to round to 1 decimal place past the original data. So we don't want 90.25, we want 90.3 would be our variance. So those are our estimates. Okay, the next thing that we will do is, let me write it out here. We want to calculate the standard deviation and variance also, but this time we're going to use the two formulas that we had previously written down in the notes. All right, so I like to do these using kind of like charts because I think it helps organize the data. You, of course, can, do this however you want. I just think that a chart sometimes makes it a little bit easier, especially if you're trying to decide which of the two methods you like better. So that's up to you. As long as you show your work, it doesn't matter to me. What is not acceptable is having answers that don't have the work that I can see to support them. So for this, whichever one you decide you like better, you can use those in your homework, but just make sure that you've shown an appropriate amount of work. So what we're going to do is I'm going to start by, actually I can't scroll that far down because I need this data here, but we are just going to make a little chart with each of the original x's first. And I'm going to use the same chart for both of them. Like I'm going to find, I'm just going to keep adding to the columns just because it's easier than writing it out twice. But with each one, you wouldn't need the same size as far as the chart. So we're going to start out, and sorry that my handwriting is so bad on this thing. It's difficult to get it looking normal. So we've got 52, 58, 64, two 72s, a 74, 76, two 80s, 82, 88, and I will have to scroll a little down, but it's okay because I'm on the last one, which is 90. So these are all my original data in my sample. And again, this was a sample from 12 adults, it said in our 3-1 notes, so it's not the population. So the next thing that we need is we need to find x minus x bar because in this guy, that's what we need to find first because that's what's in parentheses. So x minus x bar just means we're going to take each individual data value and we're going to subtract the mean. Now, of course, that requires us to actually find the mean. Now, as I said, on the quiz that covers these sections, you will have to calculate the mean and the standard deviation by hand at least once because that's assessing whether you understand how to do that or not. Since we've already passed section 3.1, I'm going to show you how to do the standard deviate or the mean in your calculator, which also subsequently does do the standard deviation, just because then you don't have to do it all by hand again. Now again, we should already know the mean from doing an example 1, but since I'm eventually going to have to show you how to use the calculator anyway, we might as well just do it now. So you go to Stat Edit, and you enter your data in the list. So remember, I've got data in my list right now. I want to get rid of it. You can do that one of two ways. You can do Stat Choice 4 and then tell it which list or lists to clear. So if I do second 1 and press enter, it clears list 1. So Stat 1, now it's clear. The other way you can do it is scroll to the name of the list, so L2, and press clear and then scroll down and it'll clear the list. I don't use that one as much because I always, for some reason, get people that accidentally confuse the clear key and the delete key. And if you delete your list, that's bad. So, okay, we're going to enter our data just as we see it here. So go ahead and do that. And of course, my graphing calculator is now frozen. So I'm going to have to see if I can fix that. Sometimes it won't fix. So I'm going to put it aside for now. Sorry about that. But right now I can't press anything. So we're just going to, for now, I guess, look at our 3 OneNotes where we already calculated X bar for the diastolic, which was 74. So that means that for each of these, and I'll go ahead and draw in kind of our row separators here. But for each of these, you're now going to go in and do the value minus 74 for each of them. So I'll give you a minute to go ahead and do that using your calculator while I'm drawing rows here. So go ahead and for each of those data values, sorry again, it's so messy, go ahead and do the X value minus 74 and record it in this column. And if you didn't pause the recording to do your work, you definitely want to do that every time I tell you to do something, so that way when you are done, you can unpause and hopefully check your answers to confirm that they're correct. So here are the values that I got for X minus X bar for each of those. Now, you'll notice that in this original formula, it's X minus X bar first, and then it says squared. So now what I have to do is I have to go through and I have to square all the values that were in this column right here. So now I'm going to have X minus X bar squared. So go ahead and take now each of these values, which hopefully you've checked to make sure they're right. Go ahead and square what you have and write it in the next column. Again, go ahead and pause this while you do that so that then when you unpause, you can check your answer. All right, so check your work on this column. Hopefully all of your answers are positive, because remember that anytime we square something, it should be positive, because a negative times a negative is a positive, and a positive times a positive is a positive. So the next thing, if I'm following order of operations, would be to take these values, and the sigma, remember, means sum. It means to add them all up. So we literally are just going to go through and add this entire column together and write the result. I usually write it down here. So in your calculator, do 484 plus 256 plus 100 plus 4 plus 4 plus 4 plus 36 plus 36 plus 64 plus 196 plus 256. And that should give us our sum. I got 1,440. Hopefully that's what you got too. So then, and I'm just going to draw it out to the side, that from the first formula, we now have the sum, which is 1440. That's the numerator, divided by n minus 1, n is the number of data pieces. In this case, that's 12, so 12 minus 1 is 11. And so our standard deviation formula here, when I take the 1440 and divide it by 11, that gives me approximately 130.90 repeating. And then if you do square root of that answer, make sure you use that answer button in your calculator instead of rounding. Because if you actually just round it to 0.9, you're going to get a different answer than if you use that second answer button. And so what we end up with for the first formula, and we round to 1 decimal place beyond the original data, is 11.4. So we have 11.4 as our standard deviation that we calculated. Now notice that that's a bit different from what we got when we used the range rule of thumb. So this is our sample standard deviation, which means then that when I take that, and again, you don't want to round the 11.4 to find the s squared. Just press the squared button in your calculator, and that way it'll be a little more accurate. Now, sometimes it might be the same thing, but sometimes it might change it, which this should make sense that it's 130.9 because the squared and the square root should undo each other. So using the first formula, this is my sample standard deviation, and this is my sample variance. All right, so now I'm going to teach you how to use the other formula, and I'm just going to continue using the columns. That way I don't have to draw them twice. But notice that it's different values that I need. So in the numerator, I already know what n is, but I need to find the sum of all the x squareds, which I have a column for the x's. I do not have a column for the x squareds. So that's the thing that I need to do next. So I'm going to just go through and take the x's themselves and square them. So 52 squared, 58 squared, all the way down the column. So again, go ahead and use your calculator to fill that out. Pause while you're doing that, and then unpause to check your answer. All right, so hopefully you got this guy. So in this formula, which again the book calls the shortcut formula, you can decide which of these two you like better. But I had all the x's, I find all the x squareds, which is pretty easy. Now I need to find the summation of all of those. So I'm going to add all of these together. Excuse me. And then I believe that you should get, when you do that, 67,152. So in this formula, then we have n, which we know is to 12. We just found the sum of all x squared, which is 67,152. Then we're going to do minus the sum of all x to the second power. So the sum of all x means I need to add this column together. So do 58 or 52 plus 58 plus 64. So go ahead and add that entire column. I don't think that one should take you too long. Believe that you should get 888. So 888 is the sum of all x. I then need to take that to the second power. So 888 to the second power, and this is all divided by 12 times 12 minus 1, which is 11. So as I simplify then, the 12 times the 67 number gives me 805824. And sorry, that looks like a 9. That guy is a 4, but I don't have an erase on this thing, so I can't try to fix it. 888 squared is 788,544. And then on the bottom, 12 times 11 gives me 132. So do the subtraction, do the division, and we should, in this case, get the same thing that we had in the original, which means we're going to obviously get the same 2 answers here. Again, it does not matter which of these 2 formulas you use. Also, I will tell you that on the quiz on this section, I will write these 2 formulas on the board. You do not need to memorize these. That is excessive. So you just need to know how to use it and to somehow show your work. So now we've got the more accurate standard deviation and variance as opposed to our range rule of thumb. All right. Nothing in this section is more time consuming than these ones. So you, if you can do those ones, you should be fine on everything else. Okay, next ones are going to be a lot shorter. Let me write them down here. Okay, so here's our next one. My brothers-in-law had diastolic BP readings of 56 and 94 respectively, and then it wants to know, are these values significant? Remember that asking if the values are significant is the same as asking if the values are unusual, or the same as asking if these values are outliers. So the way that we do that is using the range rule of thumb. And so in the picture I have drawn in the notes, we showed that, and I'll just briefly redraw part of it. But if we have our data and we have our mean in the middle, we said that 95% of the data is going to be within 2 standard deviations of X bar. So within the braces, which start at the value X bar minus 2s and end at the value X bar plus 2s, anything inside those brackets is not significant or not unusual or not an outlier. Anything that's bigger than this guy is going to be significantly high, and anything smaller than this guy is going to be significantly low. So when we are looking at this, we need to use our X bar from our data, and we need to use our standard deviation from the data. Now, because we calculated the standard deviation with the formula and with the range rule of thumb, we're going to use the formula because it's generally more accurate than this dividing by 4 formula. So we're going to use the 11.4 for our standard deviation. The X bar is still the X bar we found in section 3.1, which is 74. So that means that my lower limit is going to be 74 minus 2 times, I already forgot what it was. I think it was 11.4. Yes, times 11.4. This guy is going to be 74 plus 2 times 11.4. So then we just have to evaluate that. And so when I do that in my calculator, it gives me 51.2 here. And then on the other end, when I do the plus version of that, that gives me 96.8. So in order to be significantly low, a value would need to be below 51.2. In order to be significantly high, a value would have to be above 96.8. So 56 falls in, over here somewhere, but it is not in the significantly low. And then 94, just barely, it's right in here, but it is inside that bracket. So we would say for this, no, both values are within 2 standard deviations of the mean. All right, last one. I'm going to write the problem down first. All right, so here's our last one. We're going to pretend that our data is normally distributed. Although it does do the low, high, low, it's not symmetrical because the far left end is higher than all the other pieces on the right side. However, if we were doing a very loose interpretation of normal, then it'd be pretty close. We could probably say that it's normal if we use the loose interpretation as opposed to the strict interpretation. So what I had drawn on the board for the empirical rule is what we would be using here. So the graphic where we had the bell-shaped curve, the mean in the middle, and then I drew out the percentages for the various standard deviations. So the first question says 99.7% of the data would fall between what two numbers? So next to our empirical rule, we wrote out that this percent, 99.7% of the data should always, if it's normally distributed, fall within 3 standard deviations of the mean. So that means that if we want to know the two values, we're doing similar to what we did up here, except it's going to be 3 standard deviations instead of 2. So we're going to do 74 minus 3 times 11.4 for the lower limit, and 74 plus 3 times 11.4 for the upper limit. So we, again, are going to use our calculator for that. And that gives our lower limit as 39.8. Our upper limit would be 108.2. So we would say 99.7% fall between 39.8 and 108.2. So that's the answer to the first part of the question. The second part of the question says what percent of the data fall between 51.2 and 85.4. So again, what we had written out in class is that we know that 68% of the data fall within 1 standard deviation of the mean. And so we wrote, okay, that means if it's a total of 64%, or 68%, sorry, that means it's 34% on both sides. And again, these are approximations. It does say in everything that they give to you that it's approximately that percent. In the graphic, it gave 34.13, but it's close enough there to 34. Then within 2 standard deviations of the mean has to be 95%. So again, in the book it might be a little bit different, but 95 minus 68 is 27, and if I cut that in half, it's 13.5. So they put 13.59, but I'm just going to put 13.5% are within the next standard deviation. And then that 99.7, so all we're doing is adding another 2.7%, which means that that's only 1.35% on each side. and then the remaining percentages would be beyond that. So between 51.2 and 85.4, the first thing we need to do is figure out how many standard deviations each of these numbers is from the mean. So if my mean is 74 and my standard deviation is 11.4, I should know from the previous problem that the 51.2 is, and I'll use a different color, is this guy right here. It's 2 standard deviations below the mean. So 51.2 is right here. Our other value, 85.4, if I take 74 and I add a standard deviation, it does give me 85.4. So that would be right here. So it wants to know approximately how much of the data would fall essentially in this blue area here. So we'd have the 68% from one standard deviation, and then we'd also have that 13.5% approximately from the additional standard deviation that's only on the left side. So when I add those two together, that gives me a total of 81.5% is how much or what percent of the data we would expect to fall in this blue area. All right, I think that should cover it. Please make sure you read the post on Google Classroom for instructions with your homework.